All right, everyone, welcome to the last lesson of Unit 3 for AP Chemistry, which is going over Beer-Lambert Law, also known as Beer's Law. So Beer's Law connects the absorbance of light by a solution to three factors: the molar absorptivity, the path length, and the concentration. The equation is found in your reference sheet, and it is A equals EBC, where E is how strongly the substance absorbs light at a certain wavelength. B is going to be your path length, and C is going to be the concentration. In most experiments, B and the wavelength are constant, so absorbance is going to be directly proportional to concentration. So spectrophotometry works by measuring how much light a sample absorbs. So a light from a source is going to pass through a sample in a cuvette, and finally a detector is going to measure how much light comes out the other side of that cuvette. So the cuvette is what is holding the actual sample. So the more concentrated the solution, the more light gets absorbed by the sample and less light reaches the detector. That absorbance is then plugged into A equals EBC to find the concentration. Essentially, think of it this way. It's like shining a light or a flashlight through different glasses of juice. The darker the juice, the less light is going to come through on the other side. And the less light that comes through is going to tell you that you have a higher concentration of juice. That's the same concept with spectrophotometry. The higher the concentration, the less light will pass through. A spectrophotometer has three main parts. First, the monochromator. That is where light enters and it gets split into different wavelengths, and only the desired wavelength is going to be sent through the exit slit. And when it goes through that exit slit, it's going to go through the sample, which is in the cuvette. So the light is going to pass through that cuvette, and whatever light comes out on the other side is going to be measured by the detector. So then you can use that measurement of absorbance to calculate the concentration of that solution. In spectrophotometry, the light entering the sample is called the incident light, which is I sub 0. Some of that light is going to be absorbed by the solution as it passes through the cuvette. And then the light that exits on the other side, which is just labeled I, is the transmitted light. So the spectrophotometer measures this transmitted light, and the difference between I sub 0 and I tells us how much light was absorbed, which is then used in Beer's Law to calculate concentration. So a substance looks colored because it absorbs some wavelengths and reflects other wavelengths. For example, if a solution absorbs every wavelength except for red, then only red light is going to be reflected and reach our eyes as visible red light. So the solution looks red to us. The amount of light absorbed also affects how intense the color appears. So if the solution absorbs a lot of light, then the color looks darker and more vivid. But if it absorbs less light, the color is going to look more pale or washed out. Take a look at the color wheel here. We have our different colors in the visible spectrum, and we have their ranges of wavelengths. When we use a spectrophotometer, we often are going to choose the complementary wavelength, which is going to be what the solution absorbs the most strongly. All right, so what does that look like in real life? So let's say we wanted to find the concentration of red food dye in red Gatorade. So our first step is to fill our cuvette with red Gatorade, and we're going to run it through the spectrophotometer with green light. Now remember from our last slide, the reason we're doing green light is because if it appears red to us, that means it's going to absorb its complementary color, which is green. So if we're looking for absorbance, we want to look for the type of light or wavelength that's going to be absorbed the most. In this case, it would be green. Then we're going to look at the reading of the spectrophotometer. So it's going to tell us how much green light is absorbed in that solution. Then we can take that absorbance and we can plug it into Beer's law to solve for concentration, and that's going to lead us to the concentration of red food dye and Gatorade. All right, and I know you've talked about Beer's law a multitude of times already, but here is the slide for that if you want to pause and take a look at the details. And when we're looking at a graph of Beer's law, it is a linear relationship, meaning the absorbance of the solution is directly proportional to the concentration of the solution. So if you double the concentration of your solution, then your absorbance is also going to double. And that linear progression is why spectrophotometry is so powerful, because once we have a calibration curve, we can measure the absorbance of an unknown sample and find where it lands on the line and instantly know its concentration, which is very helpful in actual application of Beer's law. So let's talk about why sometimes we see outliers in Beer-Lambert data. One common cause, which is very tested on in AP chemistry, is fingerprints on the cuvette. So even a small smudge on the cuvette can block or scatter light, making the spectrophotometer think the solution absorbed more light than it did. So if you are looking at a Beer's law graph like we see here, and you see an outlier that has a higher absorbance, one potential outlier for this set of data would be that it had a fingerprint on the cuvette, because if there was a fingerprint there, it would absorb more light than it actually does as just the solution. All right, so let's do a few examples. So a 5.15 times 10 to the negative 6 molar solution of a red-orange pigment has an absorbance of 0.726 at 453 nanometers in a 1 centimeter cuvette. Calculate the molar absorptivity of the pigment at 453 nanometers. So we are using Beer's law here. So we have absorbance equals EVC. We are calculating molar absorptivity. So that's going to be A over BC. We know our absorbance is 0.726. Our B is our path length, which is 1 centimeter. And our C is our concentration, which is going to be 5.15 times 10 to the negative 6 molar. And when we calculate that, we end up getting 1.41 times 10 to the 5th concentration divided by centimeters. All right, and for our last question on this lesson, it says a student prepared 4 solutions of known Cu2 plus concentrations and measured the absorbance of each solution using the same cuvette. The graph shows the data for 2 absorbance measurements done for each solution. Which of the following identifies the most likely error that affected the absorbance recorded for the solution at about 7 times 10 to the negative 3rd, which is this square here? So like we talked about in a previous slide, when you have a higher absorbance than you thought you would, most likely AP is testing you on whether you understand that if you do have a smudge or a fingerprint on the cuvette, the sample would look like it's absorbing more because the fingerprint is interfering with how much light can pass through the cuvette. So the answer to this one would be B.